In this mini-series, I want to explore a hardware reversing project. I have this air conditioner which uses a remote, and we want to understand how it works. So in this mini-series, I want to reverse engineer the communication between the remote and the AC unit. It's not advanced or new in any way, it was done countless of times already, but if you have never done any electronic stuff, I think it's an awesome example to get started. I have not done this before either, I just know theoretically how it should work, so I want to take you along how I approach this project. First we try to understand the behavior of the remote and AC unit, because from that we can already infer a lot of information. And after that we will use some electronics and build a poor man's logic analyzer with an Arduino. I have here this remote with a display, showing the set temperature and other settings, such as cooling or fan modus and some other stuff. The first question is, how does the click information on the remote travel to the AC, and is there any communication back from the AC, because we can see the temperature on the remote screen? This is easy to test. We can simply walk into another room far away from the AC, change a few settings, and then walk back to the main unit and look at the display. And we can see that the settings on the main unit hasn't changed, but the remote says something else. And when we click now another button on the remote, the AC unit immediately jumps to that value. This already tells us so much on how the protocol works. Not every single press is transmitted alone. So when I press temperature up, it doesn't send an up command, it actually transmits the whole state of the settings. This means there is some kind of packet that is transmitted that contains all values. To verify this assumption, we can also change the settings on a unit and see if the remote changes, which it doesn't, and as soon as we press something on the remote, it jumps back to that value. So this reveals so much about the protocol already. It's one way from the remote to the AC unit, and it seems to be a bigger packet containing all the settings information. So how does the remote transmit this information? Well, when we look at the remote, we can see at the front what looks like any normal LED. And you probably know that that is an infrared LED. Just a quick refresher about the electromagnetic spectrum. Not that I claim to know any physics in any meaningful way, but we should have some idea about it. So visible light is a tiny area of the electromagnetic radiation. Our cells just happen to respond to those wavelengths, and our eyes are dark for all others. That's bad for a few things, so for example we cannot see dangerous gamma or X-rays, but also good because we can use the non-visible EM spectrum to transmit data. So your Wi-Fi, Bluetooth, mobile radio is all just different kinds of electromagnetic radiation. It just happens to be a different wavelength our eyes can't pick up. And infrared is also defined as a certain wavelength, which is just barely out of our capabilities to see, though there are some animals that can see infrared light. Also, most of our photosensors in our cameras react to the wavelength of infrared light. We can also point the remote at our phone camera to see that light. I can barely see it. Well, a lot of times camera use an IR filter because humans can't see infrared, thus capturing infrared could falsify the colors and stuff. I'm using an iPhone here, and I know that the front-facing camera doesn't have an IR filter, so we can see it better with that one. And also if we go into a darker room, we can really see it easily. So to properly analyze this, because it just quickly flashes, we need something that captures this. The 24 or maybe 60 frames a second of a camera are way too slow to capture the fast flickering. So we will build a small circuit to analyze this. We need a sensor that reacts to infrared light, but not other light. There are light sensors, so-called photoresistors, which increase or decrease resistance depending on the amount of light. Though this one is calibrated for regular visible light, so it's no good use to us. But I have here this IR receiver, which works more like a transistor. It has 3 pins. 2 pins are basically the power supply, plus 5 volt and ground, and the 3rd pin is either high or low depending on if it captures a significant amount of IR light or not. I put this here on a so-called breadboard. That is a convenient rapid prototyping platform. So for example, the long red and blue lines on the sides are all connected in a row, which I use for the power supply. So I can connect the IR receiver's power supply with those lines. And the holes in the middle are also connected in columns but divided in the middle, so I can plug in the IR here and it will get the power. There's also this great hobby electronics platform, which you probably know, called Arduino, which makes it super easy to use by everybody. I use an Arduino compatible board from SaintSmart because it came in this cheap electronics tutorial learning box. But you should definitely check out all those Arduino learning packs and resources. They are awesome. Those $50–60 are worth more than buying a game. You learn so much. Anyhow, this board has some pins and they are labeled. And we can see here a 5V and GND, which stands for ground pin. So we can use that to supply the breadboard with power. And you can use one of the digital input and output pins to connect to the third leg of the IR receiver. If you have never done this yourself, it might look already a bit complicated, but it's really easy. You just have to do it once yourself. Here's also the schematics of how the setup looks like. We have the IR receiver, it's connected to ground here and to VCC, which refers to the power supply. And the third pin is connected to the digital pin of the Arduino or SaintSmart Leonard board. Arduinos have this super easy programming IDE, where you can program in C and simply upload the compiled program to the board, and it just works. So we want to write some code that reads the output of the IR receiver so we can analyze it. We can take an Arduino example that would read the state of a button and just modify it to read the state of the IR receiver. So there are two main functions. The setup function, which initializes the serial communication. That's a protocol so the computer can communicate with the board and send text, and out of scope right now, but we will look at serial some other time. And we initiate the pin number 8 as an input pin. Then the loop function here is like an endless while loop. This is what will be executed constantly in a loop. And here we want to read the state of input pin 8 and send this input via serial to our computer. Then we can compile it. We have to make sure the board is properly recognized with the software, and then we can push it onto the board. Now it's running there. We can open the serial console and see the output. So currently it's sending only once, so the IR receiver outputs always high, 5V, which is a digital 1. And now we point the remote at it, and when we press it we can see some zeros rushing by. That's cool, but a bit hard to analyze. So let's modify the code to use a so-called trigger. We can start with a state 0, where we constantly read the input, and once it drops to a 0 for the first time, we switch to state 1, where we now send the input including the microseconds, so we have some timing information as well, to the computer. Now we push it to the board, wait until it's booted, and now we see no input being sent to the computer. But if we point now the remote at the IR receiver and press the button, we get the first 0, and now the data is rushing in. That's better. Now we can simply copy this output into a text file to analyze. We can now collect multiple samples, for example the packet to select Fahrenheit or Celsius, or turning it on and off. Then I use Jupyter notebooks to work with stuff like this. It's basically Python, just with an awesome interface to do explorative scripts. I first start by including some important modules so we can plot data. And then we read one of the log data files with NumPy and specify that the data is comma separated. This will give us a big NumPy array, and we can then extract the microseconds into single bits. Next we can use pyplot to plot this data in steps. Looks a bit awkward, so let's play around a little bit with the limits of the y and x axis, as well as the figure size of the plot. And maybe also cut the data points at some length, because we only are interested in the data at the front. We might want to add some points, so we can see exactly where our data points are. We can now also wrap this into a function, so we can simply call load with a file name and get this nice digital logic plot. Awesome! Look at this. This is great. This is a great poor man's logic analyzer. And we can compare, for example, Celsius to Fahrenheit packet and the on and off packet. But how do we read this? They clearly look similar, so this is not some random wiggling. This is some kind of real pattern. This is the infrared LED flickering on and off in a specific way. But how the LED flickers is defined in the protocol, and somehow we have to understand how the protocol works. So one attack you can do without knowing the protocol is compare multiple packets of the same command, like multiple turning on packets, and then you could see that this is always the same. So there's no crypto or timestamp or whatever involved. So a replay attack is easily possible. Without knowing what the bits mean, we can just resend the pattern to perform this action. Another thing to work out the protocol is to compare similar packets, like Celsius and Fahrenheit. And we notice that some spikes are very close together and some spikes are far apart, and we can try to see if this pattern is different for both of them. Because Fahrenheit and Celsius can be represented by one bit, it's either 0 or 1. We can infer from that what a bit 0 or 1 might look like in this pattern. Maybe you can pause this video here and try to extract the single bits from those packets. But there's a big problem here. Each single dot is a point where we read the state of the receiver, and they are so little compared to the amount of spikes. Thus maybe we miss some spikes, or some spikes appear wider or thinner even though they were the same. In proper terms, we have a way too low sampling rate for the frequency of the input signal. So this Arduino and laptop setup is a great start, but it's not very precise. It is enough to work out the protocol, but next video I want to show you how you can do this a little bit more advanced, and we will start reversing the packets.